this first one. But this is a pretty classic type of a gas problem. I like saying gas problems because it sounds like parts. But if you have something like this, how do you solve this? How do you figure this out? There's a couple ways to do it. How did you do it? Yeah.
I would solve for moles.
Okay.
So when I have the moles.
So we always have this ideal gas law, and we're given an initial temperature, pressure, and volume. So we can solve for moles. If one of those things changes or multiple of those things change, moles always stays the same. So we can always kind of leave moles the same and then solve for the new unknown. Does anybody do it differently?
You do PV equals P2.
Yeah, you can kind of, remember how we had that shortcut for concentration, the M1 V1 equals M2 V2? Because we could say M times V is always moles. So if moles are the same, then M times V is always going to be constant. It's the same idea here. We can rearrange this expression to say PV over T equals NR. NR is basically constant in this type of a problem because we're not changing the number of moles of gas. We're just changing the pressure, volume, or temperature. So that means the pressure, volume, temperature together, pressure times volume divided by temperature, always has to be constant. So another way that we can think about that then is that given an initial pressure, volume, and temperature, if that has to be constant, assuming moles are constant, we can have this kind of a relationship. And that's essentially doing exactly what you just said, that you're solving for moles and then plugging them into the new equation. But if you can think about it this way, it might save you a step, because now we can just say, we can just plug these things in accordingly. And in this case, I'm not even sure we have to convert pressure. Yeah, we would not have to convert pressure in this case, because we've got the same units on both sides. So we still have to convert temperature to be in Kelvin, but pressure we can leave in torr as long as it's the same on both sides. So let's see if that works, actually, because I'm pretty sure that's the case. So 248 times 275 divided by 125C is what, 398 K, right? And that has to equal our pressure that we're solving for times 321 liters divided by that same 398. So if we solve for P2, I don't have it up yet. So if we solve for P2, that's going to be 248 times 275 divided by 321. Oops, I hit a button right here. 248 times 275 divided by 321. 212 torr, is that what you got? So if you did it a different way, is that what you also got? Okay. The other thing I just realized doing this is you'll notice that the temperature doesn't change. If we're at constant temperature, this is really just a Boyle's law problem. Right? We're really just saying PV equals PV because temperature doesn't change. Okay, good. Any problems with that one, or things you ran into, maybe even troubles you ran into that you then figured out? No, everything good? All right. What about this next one? How do you find density of a gas in grams per liter? And let's say you forgot that, let's say you forgot the equation that we talked about yesterday, where you can have the molecular weight, you replace it with the molecular weight and density, kind of that other version of the ideal gas law. How could you solve this if you didn't remember that equation? I guess, did you use that equation when you solved it? Okay. So how could you do it if you didn't remember that equation? You can actually make it a much simpler problem than that. You think about what does it mean to, what does the density mean, and then what does it mean to be at standard temperature and pressure? That might be a shortcut that you can use there.
You use the constant volume.
Right, you can use the molar volume, because we know to find density, we need a mass and we need a volume of the same amount of stuff. So if we have, let's say, a mole of argon, do we know how much a mole of argon weighs? We can probably figure it out, right? It's up on the periodic table, 39.948. That's how much a mole of argon weighs. Do we know how much space a mole of argon takes up? We do, 22.41 liters at standard temperature and pressure. So density, we can say, all right, for 1 mole argon, we're going to have 39.95 grams over 22.41 liters. Is 1.78 grams per liter. So there was no need to bring in all that other gas law stuff because standard temperature and pressure, we know the molar volume. It's another trick you can use. I don't think we have an exact example of that here, but you can use that molar volume elsewhere also. If you know you have a mole of something or a fraction of a mole of something, you can turn, and you don't remember that other equation, you can go back and use these kinds of relationships when you know that one of the volumes might be 22.4 liters if it comes up in a problem. Okay, so let's try a couple more that are, again, same kind of uses, same kind of ideas, but a little more context inside solving for some other stuff. So if you haven't already, go ahead and try these two. First, we're going to talk about collecting a gas over water and calculating a mass, and then using methane in an equation, an unbalanced equation. Keep in mind here. This is similar to one that we did last time. Perfect. say that. It doesn't say that we collect a certain amount of hydrogen peroxide. So you don't know if you have a volume, a temperature, and pressure. You better leave for to get those things.
Oh, you
How confident are you about it?
can I explain?
Yeah, it's okay. Well, what do you think? The total pressure is oxygen and water. So if you want to know what mass of oxygen is which is yes, water pressure.
So it would be
Yes, you just subtract that out first. All right, should we look at this first one? So how'd you go about this one? Where'd you start? Got to find moles. So is that just PV equals nRT and solve for moles? Okay. A couple things we have to do first, though, to correct that. So yes, we're going to solve for moles, which is this. But we can't just plug those numbers in as they are, right? We have to do some conversions and some corrections. So how do we correct for the pressure? Make sure we have the correct pressure here.
Divide by 670 and then subtract the pressure of the water.
Yeah, we gotta do two things. We gotta subtract for the pressure of water, and divide by 760 to get from torr to atmosphere. Because it's collected over water, that means that 742 torr in the chamber contains both oxygen and water. Since we only care about the moles of oxygen, we have to subtract that oxygen or that water out, so we only have the pressure of the water. So pressure of oxygen. Pressure of oxygen is going to be the total pressure, 742 torr, minus the pressure of water, 24. And that's going to be 728. No, 718. So that's what we'll now convert to atmospheres by dividing by 760 to get our pressure for the equation. So we've got our pressure. Our volume, again, is in milliliters, so we need to convert that to liters. That's easy enough. Now we've got our R. And our temperature, which we also have to convert. All right, so 0.945 times 0.0753. Call that 2.91 millimoles of oxygen. So to convert from millimoles to milligrams, we divide, or we multiply by the molar mass, which is 16 milligrams per millimole, or 32 milligrams per millimole. .12 milligrams, which is B. I guess since the answer was in grams, we probably should have just kept it in moles and then converted to grams that way. Either way. So what you got? So you notice, I think I saw this in somebody's, if you forgot to correct for the water pressure, I think that was D. So that was still one of the answers that was listed. So if you didn't see that, and that's common with these multiple choice questions, that whoever writes the questions thinks about the most common mistakes, procedural mistakes, and then makes answers that you would get with those procedural mistakes. So just because your answer shows up in the multiple choice doesn't mean it's right when you're doing a calculation. Oh, so Julie. Okay, let's look down at this reaction then. Did anybody get this equation balanced? How do we balance this? Something like, oh, it's just balanced, isn't it?
You have to put in 3
From H2.
Oh, okay, I see it, yes. There, now it's balanced. Yes, okay. So we're synthesizing carbon monoxide and hydrogen. And we've got, this time we're given the amount of methane that's so we start with, rather than the amount of product. So we have to still go through and do the stoichiometry here. All right, now how did you go about this? Did you try this one yet? Did you try this one yet? Yes, no, maybe, yeah, no. Okay, give it a try. Now we get a balanced equation, see what you come up with. If you already did it, I don't know, go on or screw around on your phone for a little bit. Yeah. So if you're given 275 liters of methane, how do you convert that to moles? How do you figure out moles? So you can do the equation.
About 22.4.
Right, we're at STP, so we divide by 22.4. What if we weren't at STP? How would you do it? How do you find moles not at STP? You just have to do the equation, right? You just have to put in the pressure and the temperature and whatever else. But since we're at STP, we can go 275 liters times divided by 22.4 liters in 1 mole. Get 12.3 moles of methane. So if we've got 12.3 moles of methane, we're going to make 3 times as much hydrogen, right? Because the equation tells us they react 1 to 3, 1 methane for 3 hydrogens. So that means this will be 36.9 moles. Of course, the question asks what mass of hydrogen. So we multiply by the molar mass. $24.5. Well, that's probably the closest, right? I don't know why we're off so far from the rounding error. Still right. Did anybody get something different? Okay. I think I did it right, but I don't know why that number is not closer to what we got. Okay. All right, so moving on. I saw some of you getting started on these, so that's great. Let's look at these. So this next one is a little bit different in that it's talking about making a solution. Remember we talked about hydrochloric acid is hydrogen chloride dissolved in water. Hydrogen chloride is a gas. So if you have a certain quantity of the gas and you dissolve that in water, what's the concentration? Now, you have to assume in a question like this that the volume of HCl is 0 when it's in solution. Because remember that molarity is moles of solute per liters of solution. That's a reasonable estimate when you're talking about a gaseous solute because it's going to be relatively small and not take up a lot of space. But really we need to know the overall volume of the solution. And this question should have been worded in such a way that said something like forming 5.25 liters of solution rather than talking about 5.25 liters of just water. So what do you think we need to find first? Moles, because molarity is moles per liter. So we need moles of HCl, then we can just divide by the volume, and we've got our concentration. So we're going to use our standard gas law to solve for moles. We do have to convert from kilopascals to atmospheres if we want to use our R that we know. Does anybody know what that conversion is? Top of your head, or did you look it up? I think it's like 101. Does that sound right? They may have that. Yeah, really good. I think it's 101. It means 101 kilopascals in an atmosphere. Let's check it. Is that right? Okay. Yeah, 101. So 89.6 divided by 101 is 0.887. 310, right? So I come up with 7.84 moles HCl. Is that what you got? Everyone's just sort of blankly staring at me. So I guess yes. Okay. So we divide that by the volume. And that should be our concentration, 1.49 molar. Well, molarity is moles per liter. So that's 7.84 moles per 5.25 liters. Yeah.
For the pressure, you said something about the pressure, right? No.
Yeah. What about it?
How do you know that the pressure is 0.8?
Because it's given in kilopascals, 89.6 kilo. To convert it. That's not a conversion that you need to know off the top of your head, but it's one that you could look up. Another option, if you want to speed things up with these, because of these pressure conversions, torr is just as common, or millimeters of mercury, just as common of a measurement for pressure as atmospheres, especially when we're dealing with gases. So some people like to actually remember an R that reflects that. So this R is in liter atmospheres per mole Kelvin, liter atmospheres per mole Kelvin. But if we multiply that by 760, we would have liter torr per mole Kelvin. So 0.0821 times 760 is 62.4, we'll say. So 62.4 liter torr per mole Kelvin. And so if you want to remember that number 62.4, you could plug that in as your R when you're dealing with torr, and then not have to actually convert the pressure. If that's confusing, then don't worry about it, just convert your pressures, but that is another option. It's the R that controls that. You could also have a kilopascal based R, which we often use for other calculations that you'll do in future chemistry classes. All right, and then we talk about effusion. We talked about that a little bit in class just briefly yesterday. What is it again? What does effusion refer to? Better remember?
How quickly a gas goes through a small hole.
Yeah, how quickly a gas would kind of like escape through a small hole. So when you encounter effusion in things like the our exams or like the final national exam, they usually won't ask for specific calculation because I don't know, it's just not that important of a calculation. But it is important to know what effusion is and what affects it. So given this list of gases, which would you expect to effuse most rapidly? And why?
Nitrogen.
Why nitrogen?
It's the smallest.
Yeah. Yeah, so this is just a matter of size, particle size. It's proportional to mass. It's proportional to molar mass. Effusion is proportional to molar mass. The greater the molar mass, the slower it effuses. So nitrogen will be the fastest. We can actually rank them, right, based on molar mass. So this one is, we've got 28, oxygen's 36, HCl is 36.5, and ammonia would be 17. So should be ammonia, right? So ammonia is actually the fastest diffuser because it has the lowest molar mass. Sorry, I didn't even see that one in there, so I was thinking about it. So we would go ammonia, nitrogen, oxygen, and then HCl. Should be 36.6. All right. Same idea on the back. You probably won't be asked to calculate a root mean square molecular speed or velocity, but you should know what it means and why it's important. And so a question like this is something that you should be able to answer. So which substance has the highest speed at 25 degrees C? And what are you looking at for that? What determines molecular speed? Well, let's look at temperature. So temperature, remember, is proportional to 1/2 mv squared. That's the kinetic energy. So the higher the temperature, the higher the kinetic energy. But if temperature is constant, like it is for all of these, then it's going to be proportional to the product of the mass and the square of the velocity. So which one goes the fastest? If they all have the same temperature, which has the greatest V? How do you make that distinction? Yeah, the one with the smallest mass. So if M is smaller, then V has to be bigger to compensate if we have the same temperature. So smaller at the same temperature, a smaller particle will go faster than a larger particle. So of those four, which is the smallest? C, yeah, hydrogen's smallest. So that one's going to have the greatest molecular speed. And then I want to go over this one more time because we just kind of blew through it at the very end last time. But nitrogen will behave most like an ideal gas, and this is true for any gas. Where is it most like an ideal gas? Where does it deviate from ideality, and why? Do you remember the two reasons why, or two situations when gases start to be not ideal, and why? What are the two things that affect that in gases? I'll give you a hint. One of them has to do with pressure, and one of them has to do with volume.
Extremely high pressure.
Yeah, what happens at extremely high pressure?
The collisions aren't elastic anymore?
Right, the collisions aren't elastic anymore. At extremely high pressure, the molecules are too close to each other, and so the, not even extremely high pressure, like somewhat high pressures. Actually, wait, that's not right. Temperatures, right? Extremely low temperatures, the molecules aren't moving very fast, so their attractive forces become more important, and their collisions are not elastic anymore. So at low temperature, you would not have ideal gas. Sorry, we're backwards with that. It's temperature and volume. High pressure is another situation, but is another situation where you won't have as much of an ideal gas. But it's not because of the collisions. Why is it? Why does it deviate from ideality at high pressures?
There's a lot more moles in that space, so the size matters more.
Yeah, the size starts to matter. The volume, we can't assume that the gas particles take up no space anymore. Because at really high pressure, the gas particles actually are a significant part of the volume. And so that starts to deviate from ideality. So a gas will be most ideal at high temperature and low pressure. And let's check ourselves on that. We'll pull up the notes from yesterday. You can see at the end here. You see at high pressure, volume is higher than predicted because of the space that the individual atoms or molecules take up. And then at low temperature, the pressure is lower than predicted because of the intermolecular forces, because of the inelastic collisions. And the fact that the gases are kind of pulling each other toward each other. All right. Okay, two more good stoichiometry type problems. So let's see if we can work these out now that we've practiced them. None of these I don't think are anything new, except that there may be some limiting reactant type stuff happening here. In 84 at least, probably not in 85. So now that we've done a couple of these, give it a try, see if you can come up with the answer. There's no multiple choice here, so you just gotta solve the problem out. All right, how do these go? Maybe okay. Sort of get the idea. But these, I mean, these are the typical types of things that you'll see on an exam. Because an exam usually brings in multiple things, the only difference is you'll probably not see balanced equations. So you'd have to come up with the balanced equations yourself based on the formulas, especially for something like 84, where you could kind of predict that as a single replacement reaction, kind of like the ones we've done in lab. 85, you wouldn't necessarily know the formulas for glucose and ethanol, so those would probably be given. All right, let's look at this first one. What did you come up with? How did you start this one? What did you have to find first, or second, or at the beginning anyway?
Limiting reactant.
Right, we got to find the limiting reactants. We got to figure out moles of aluminum and moles of HCl. Moles of aluminum we can get dividing the mass by the molar mass, so 10 grams by 27 divided by 27, 0.370 moles. And HCl, we get the moles from the molarity. We've got 6 molar, 100 milliliters. So that's 0.6 molar, right? 0.600 moles. Is that what you got? All right. So what's the limiting reactant? Yeah, it's got to be the HCl, because we need 3 times as much HCl as aluminum. We've got 0.37 moles of aluminum and 0.6 moles of HCl, which means for 0.6 moles of HCl, we need 0.2 moles of aluminum. We have more than that, so we have some excess aluminum. So we're going to do our calculations based on this one as limiting. All right, so the volume of hydrogen that can be produced, we don't actually have to go through the whole gas law here because we're at STP. So they made it nice for us. 6 to 3 means we make half as many moles of hydrogen as we had HCl. So that's 0.300 moles. And then 0.300 moles at STP is 0.3 times 22.4. That's 6.72 liters. Is that what you got? Like that? See a couple head nods. Now you could go through the whole thing with, calculating the molar ratio and then plugging it in to the ideal gas law. That's totally fine. You should come up with the same answer. I just took a couple shortcuts to make it go a little quicker. And then this last one, yeast converting glucose to ethanol and carbon dioxide. What volume of carbon dioxide measured at 745 torr and 25.0 degrees C can be produced by the fermentation of 10.0 grams of glucose? All right, so in this case, we've got just one reactant, so we can just calculate moles and then get carbon dioxide. And this time we will have to use the ideal gas law because we're not at standard temperature and pressure. Okay, got our balanced equation. What's the molar mass for glucose? Anybody find that? Okay. $180. Okay, I'll trust you on that one. So we've got 10 grams. 10 divided by 180 is 0.0555. It's 1 to 2 with carbon dioxide with moles, so we have to double that to get the moles of carbon dioxide. So that's 0.111 moles of carbon dioxide. Or really 111. No, 0.0556. I was going to say that doesn't make sense. Okay. So 0.111 moles. And then we solve for whatever it's asking for, volume. Liters is RT over P. So we've got 0.111 moles. Temperature is 298 K. And the pressure is 745 torr, which divide by 760, and we get 0.980 atmospheres. All right, let's calculate this. 0.111 times 0.0821 times 298 divided by 0.98. And I get 2.77 liters. Is that right? Great. So just like anything else, these problems require practice. Hopefully after today you've got a sense of that. So we've got about 15 minutes left. I will just want to pull up a couple of things to show you, one of which I don't have here, so hang on a second.